Okay. So how does the story go? With Newton's method, do you remember with IVT you had to find an interval? With Newton's method, you don't have to find an interval. You just have to find a point to begin with. So you start with a point to begin with. Let's see. And let's see, this is point x0. That's a start point. Then you choose x0 if you are able to kind of guess where your 0 is, close to the 0, close to the root. In this case, it's not very close, but I need to be further away so I can explain it, right? And then from x0, find the x0 and f of x0, which is a point on the graph. Then find a tangent. And then find a point that tangent touches the x-axis. Call that x1. Okay? Then from there, find fx1 and f of x1. Draw the tangents there. And then find the point that tangent touches the graph again, x2. And so on. As you're doing this over and over, you realize that you're getting closer to the 0, basically. It sort of takes you to the 0 of the root of the function. Is that always the case? No. What you need to do, there's so much in here that I sort of can explain, but it's wave-handy explanation. Right? So what I do is I give you one example of this thing. I just drive the formula, give you one example. You do a couple of examples in the class, it's just numerical, and then you do the comparison and come up with some ideas. But I just don't want to give you the wrong idea, because some of the ideas you come up with are not going to be very accurate. It's semi-accurate. But it's, at this point, that's all I can do, right, as this course, basically. So, again, even with polynomials, we only have quadratic formula, then we have formulas for cubic, then I think for quadric, and then 5 and higher there's no formula. And cubic and quadric, ask me, I have no idea how to do them. There's a few pages long, the formula. Just that many pieces, basically. And so there's always a numerical method that we use to find the solutions for these things, right? To find the roots. Now here's the formula here. Let me go back to the picture I drew, because it's already there. You start from an x0, you try to be close to the root. Then you go up there, you get x0 and f of x0. Then you find a tangent line there. What's the tangent line? Y minus f of x0 is equal to f prime at x0 times x minus x0, right? Now, here I'm saying the tangent line, where tangent line touches 0, touches x-axis. That means y has to be 0. So that means that what I have is 0 minus f of x0 is equal to f prime of x0 times x minus x0. If I want to solve for x, I'm going to get x is equal to minus f of x0 divided by f prime of x0 plus x0. I can put the minus there or can put it here, either way. So this gives me that x1 is actually that. x1 is x0 minus f of x0 over f prime of x0. If I follow this routine, I will figure out that x2 is equal to x1 minus f of x1 over f prime of x1. And so on and so forth. So it's a successive way of finding x. Every time xi xi is going to be a function of the xi minus 1, right? So basically, every successive x is going to be a function of previous x. This is also called in Calc 2 a sequence. So you find a sequence, and they are basically successive sequence of numbers. And if they converge to a root. Now, given this formula, and I'm saying da 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 da, so basically the overall formula looks like this. It looks like x I plus 1 is equal to xi minus f of xi over f prime of xi. For this formula to work, this darn thing has to be non-zero, right? So at any point, if you hit the critical point, you have to get out. So no critical points. Xi cannot be critical point. Some of the things that are not very good with this method. Now, this picture you may have seen before. It's just, it tells you I start at x0, then I go up to the graph. From the graph at x0, f of x0, I draw the tangent line. Let the tangent line touch the x-axis. Do you guys see tangent line is touching the x-axis? Choose that to be x1. From x1, go back up to the graph. Draw another tangent line. That tangent line goes again down where it touches x-axis, call it x2. And then again, and again, and again, and you see that it's getting closer and closer to that 0. Do you see the cyan point is the 0 of the, so it gets closer and closer. And it works for a lot of stuff, and it works fast. It's not as clumsy and slow as the bisection method was. So that's a nice part of it. But bisection method almost ensured it. I mean, if the conditions were satisfied, you knew you can get too close to the root. This one you don't know. So now, let's try to find. I do only one example. You guys do 3 examples just like this in the lab, basically. So approximate square root of 5 using f of x equal to x squared minus 5 with starting point of the sequence equal to 2. Okay, so let's just go back. Is square root of 5 root of that? Yeah, because if I solve it, I get square root of 5. But I don't have any decimal values that way. I have to find the decimal value. And so one of the ways is that to use the Newton's method to find the decimal value. So how do we go about this? First of all, I have to set up this equation. So first, let's find f prime of x. And that is 2x, right? So according to that, xi plus 1 is going to be equal to xi minus, what is f? X squared minus 5 divided by 2x. So for this problem, that's the recursive or successive formula. That's a successive formula. Oh, sorry. Yeah, I saw a few faces. There were an I in here and I in there. Xi. No x, all xi. So this is the successive formula. That means that I have x0 also. That means that x1 is equal to x0 minus x0 to power 2 minus 5 over 2x0. That is 2 minus 4 minus 1 over 4, right? Minus 5. There we go. And so it's 2 plus 1/4. That's 2.25. Now, let's compute x2. x2 is equal to x1, again, this in the same problem, minus x1 to power 2 minus 5 over 2x1. Everybody agrees on that? Now, what is x1? x1 is that. And times 2 dot, which is 2.25 divided by minus 6.25 minus 5 over 4.5. That's 2.25 minus 1.25 over 4.5. And if you think I'm going to compute that, no, you're wrong. And so it's approximately equal to 2.3607 and so on. It turns out, after 2 tries, yeah, I need to do more to make sure it's happening, right? I need to know more to see that the points are getting closer and closer to each other. But after 2 tries, it's a waste of my time right now. So because I'm just telling you this story. I mean, computing them one by one. You want to compute it to know it's happening, basically. And here, I see that this is actually very close to the value, computed value that I have for, oh, that other one was 6.1. Yeah, it wasn't that close. Yeah, there we go. So the 2 of them are pretty close. That's the actual value that people computed through the method. But after 2 tries, you're already very close to that. This was not the case with bisection, right? So it's a fast method, but it's not as reliable as bisection. Fair enough? Yeah. And so if I wanted to get the negative square root of 5, I should have started in a negative area, closer to that, to get to that root. And it doesn't always work that way neither. That's another problem. That's why it's not very reliable sometimes. There are theorems, do you guys know what open questions are? Open questions in mathematics are questions that nobody knows the answer. So there are open questions related to Newton's method. So there's like a lot going on. And that's, I think, good enough for us at this point. And yeah, basically we can do a little bit more. We can try different values and compare how it converges and stuff like that. And then we can discuss this type. There are like functions like that. You can see that tangential line is just getting away from the 0. So starting point becomes really, really important. And that's not good for us. We want to be able to just go at any point and hit the 0 anyway. And that is not the best choice in here. Do you want to do this one? Where'd it go?